Welcome to the Nolan Ryan Junior High Hack the Science Staar Champions of Science. We're going to get started today with looking at our periodic table, and we are going to begin with doing what we should always do when we get a periodic table. We're going to start with circling ape and man. These are the two we are going to circle in the box, the element box that has been taken out, just to give you some information. So the top number, the atomic number, is our A number, atomic number. This number is equivalent to the number of protons an element has, as well as the number of electrons an element has. Remember that protons are positively charged and electrons are negatively charged. And the bottom number, the mass number, atomic mass. Mass, we're going to let that stand for M, our man number. That's the M in man. Minus A, the atomic number, would give us the number of neutrons if we needed to calculate the neutrons that are found in an element. Neutrons are neutral. Okay, if we wanted to draw a diagram of this element using the information we have gained here, we are going to start with what is inside the nucleus. Here's our little model. Here's the nucleus. Inside the nucleus is always, you will always find the protons. Which, how many of them are there? Well, if there's 14 as the ape number, then there are 14 protons and 14 electrons. So P is equal to 14. And inside the nucleus, you will also find the neutrons, which are neutral or no charge. And we don't know how many neutrons there are. We're going to have to calculate that. Remember, when we use the mass number, we have to round it to the nearest whole number. In this instance, it would be 28. We're going to subtract the A number, which is the atomic number, the top one, 14. And that will give us the number of neutrons. So the neutrons in this instance are going to be 14. There are 14 neutral neutrons inside the nucleus. Before I continue with our model, I do want you to know that the most mass of an element is in nucleus. Why? Because the protons and neutrons are large particles. If y'all remember correctly, they had each one of them an atomic mass of 1 AMU, or 1 atomic mass unit. And if you remember correctly, the electrons are very tiny. In order to make up 1 proton, you need 1,834 electrons. So that's quite a bit. So we need to continue on. We are now going to begin our electron cloud, which is outside the nucleus. If you remember, we have orbitals or energy levels in the electron cloud, and there's a certain way we can place our electrons on them. Remember, we use the 288, the Highway 288, Super Electron Highway 288, to remember how to place electrons on the orbitals. So we're going to start with the first orbital, which only holds 2 electrons. So let's go ahead and do it. 1, 2. We have a total of 14, right? Remember, ape is equal to protons and electrons. We know we got 14, so we got 2. We're going to have to draw us another energy level. And if we fill it up with 8, 8 plus 2 is 10, so we're going to need a third. Let's put these 8 on there. All right, and then we're going to need 1 more energy level, which also can hold only 8, but now we have 2 plus 8 is 10. 10 minus 14 is 4 left. So 1, 2, 3, 4. Okay, so that would be a model of the atom of silicon. Now, if you are trying to identify a model, a Bohr model like this, most likely you will not be given this information, so this won't be there. There'll be, big circles and indicating protons and neutrons in the nucleus. So you can't count the protons, even though the protons do identify the element, but you can't count them because you can't see them all inside the nucleus. But you can count the electrons, which are equal to the protons. So if you know, oh, well, this has 14 electrons because I've counted them, I can see, okay, so 14 electrons should be equivalent to the atomic number, which is the top number in the box. So I know if I find the box with 14 in it, I have now figured out what my element is. This one is silicon. Let's see if we can try that again, looking at this model. On this model, as you see, inside the nucleus, you do have particles that have protons, the positive charge, and you can see the neutrons are in there as well with no indicator of charge, and then you see the electrons have the little minus for negative charge, but we can't see all the protons in here. So we can't use this as a reference as to figuring out what element this is. But we do see all the electrons, so we're just going to count them. 1, 2, 3, 4, 5, 6, 7. We have 7 electrons. So I'm looking for an ape number that is equal to 7, right? Because they're all equal. So now all I have to do is look on my periodic table, make sure that top ape number is 7 in the box, in the element box, and then I'll know. And if I look, here it is, and we have identified our element. Our element is nitrogen. Okay, so we're one step closer to getting where we're going. We are going to add to our periodic table here at the top that the protons, or the ape number, determine the element's identity. So if we know the ape number, the protons or electrons, we can definitely find our element. All right, so let's continue on. Let's look at the overall periodic table. We know that the periodic table is a wonder chart. It really is for chemistry. The first thing that we need to remember is that this stair step actually separates our metals from our non-metals. So I'm going to extend it here, and I put the metals are basically to the left and the non-metals to the right. Along the stair step, though, you find what is known as the metalloids. So here at the bottom, I'm going to go ahead and extend this and put a little arrow here saying that metalloids are touching the stair step. Metalloids touch stair step. Okay, there is an exception to that rule, the exception being what element? If you guessed aluminum, you're absolutely correct. Aluminum is a metal. And there's also another exception to our periodic table. If we go all the way to the left side, the very first element in the first group is hydrogen. Hydrogen is a non-metal, okay? Just so you remember that. All right, so let's do some characteristics of metals and non-metals and refresh our memory. Metals are conductors of heat and electrical or electricity. Metals are shiny, they have luster. Metals can be flattened or hammered into sheets, such as aluminum foil. We call this property malleable. And metals can be pulled into wires. We refer to that as ductile. That's pretty much the main qualities of the metals. The non-metals, on the other hand, are brittle solids, meaning that if they're solid, they are very breakable. Most are gases. And they do not conduct. They are basically insulators or non-conductors. I'm going to put insulators. Now if we go back down and talk a little bit about our metalloids, those touching that stair step, they actually have properties of both metals and both nonmetals. So have properties of metals and nonmetals. Here's where you would find things like semiconductors. They conduct sometimes, and others they do not. Okay. All right, let's continue on. Let's look at some more properties of our periodic table. One of the things that you'll notice is there are numbers going across, and there are numbers here to the side. The numbers here to the side are what we refer to as periods. They are the rows on the periodic table. Each period gives us information about the elements in those rows. So one way I remember that these are the periods or the rows, I think about how a sentence is with a period, and you always write your sentence from left to right, and you end with a period. So that would be one way to remember that these are the rows. So what does a row tell us about elements in those rows? It tells us how many energy levels they have. So if I am in row 1, and if you look at it, row 1 only has hydrogen and helium. Those are the only two elements in row 1. Row 1 has 1 energy level. So hydrogen and helium both would have 1 energy level. Row 2 has 2 energy levels. So every element in row 2, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon, all have 2 energy levels in their electron cloud, right, outside the nucleus. And it continues that way. So row 3 has 3, 4 has 4, and so forth and so on for each one of these rows. How many energy levels or electron orbitals can an atom have at most is 7. That's where it stops. If you look down here, you can see that these 2 rows have been pulled out of these 2 rows. So this, it belongs to row 6, and this belongs to row 7. Each having either 6 energy levels or 7. 7 is the max an element would have in energy levels. All right, so let's look at the numbers at the top here. At the top here, we have 2 numbers over each column. The first number, and I'm going to circle them all in red. So all the way from 1 through 18. The top number is the group number. Groups are a family number. So everyone in a row together, they share similar properties. These are our groups. One way to remember these, they go up and down, groups, and they are like families. Some people call them families, element families. And why? Because they share similar properties. Okay. All right. There is a bottom number under each of the family or group numbers. These bottom numbers give us also some additional information about the elements in those families. We're looking at only the A numbers. We'll talk about that in a minute. This is the number of valence electrons, and if you remember from when we learned about chemistry, and we're going to write that up here, valence electrons determine what? Valence electrons determine how an element will react, so reactivity. Reactivity just means bonding. Will they bond or not with another element? Remember the valence electrons, if you remember, they're the outermost electrons. So 1, 2, 3, 4, this outer shell, outermost shell has the valence electrons. It's also known as a valence shell. All right, so we see 1A, 1 valence electron, 2 valence electron. Now we come back down here and we see all these B's. Well, these are a special group of metals. These are known as our transition metals. And they do not follow the rules that we are fixing to talk about of bonding. They're a little different. So we leave them out for now. Just know these are transition metals. But we're going to do 1 valence electrons, 2 valence electrons, skip a few valence electrons, and go all the way to 3, or family or group 13. It has 3 valence electrons, 14, 4, 15, 5, 16, 6, 17, 7, 18, 8. Now let's just make a little note. Once again, these are valence electrons. Okay. So, yes, valence electrons determine the reactivity. And if you remember correctly, let's scoot down here to the bottom for a second. Remember, valence electrons, every element wants how many outermost electrons? They all want 8. Because 8 is great. Now, we just looked at some. We looked at group 1. They only have 1. They need 7 more. 2 wants 8. They need 6 more. So these elements in these families are going to find other elements to bond and react with to get to 8. So let's look at the basics. The most basic way they bond is group 1 and 17. Why? Because 1 has 1A, 1 valence electron. 17 has 7. 1 plus 7 make 8. So they'll like to bond. Group 2 and 16. 16 has 6A, or 6 valence electrons. 2 has 2A. They make together 8. Group 13 has 3. And it wants to bond with 15. You got it, because they have 5. And together they will make 8. And group 14 will bond with members from its group. Now, is this the only way elements bond? Absolutely not. This is just the most basic way they can bond to get to that wonderful number 8. Now, obviously, we left a group out. We left out our, y'all remember the name? What are these called? These are the noble gases, right? Our noble gases, they have 8, right? They have 8 valence electrons. So noble gases do not react, do not bond, or react. Means the same thing, bond, react. They have 8 valence electrons. We've also referred to them as stable elements or inert because they are non-reactive. Okay? All right. So let's think of what could possibly be some signs you would see of a chemical reaction. Let's go up here to the top corner and let's list some signs of a chemical reaction. What are signs of a chemical reaction? Let's see if we can remember. That don't work. Another one. Signs of chemical reaction. Y'all remember any? This was what you would see when elements bond. Well, if you remember correctly, we have the first thing, the temperature might change, or the temperature will change. That is a sign. It will either decrease, go down, or it may increase, go up. That is a sign of a chemical reaction. When you mix two things together and this happens, you know a chemical reaction occurred. Another sign is gases produced. You see bubbling. That's the formation of a gas. I'm going to put bubbling, fizzing. When you mix two things together and you see that occur, you know a chemical reaction has occurred. Okay, a distinct change in color, meaning that if you mix two clear liquids like we did at one point and you come up with a bright yellow, you definitely have a distinct color change. You get a color that was never there before. So that would be that. If you have a distinct odor change, for example, you get the milk out of the fridge and it stinks, has chunks in it, smells really bad. It is no longer milk, guys. It is sour milk, truly, and it has undergone a chemical reaction, and that's why there is such a change in odor. If light is produced, fireworks, when we burn the metal magnesium and it went bright, bright white light, that is a sign of a chemical reaction. And then we also have, last but not least, when a precipitate forms. Precipitate is a solid that forms out of nowhere. So you pour things together and all of a sudden you had two liquids initially. Now you have some liquid and a solid. That is a precipitate, and that is another sign of a chemical reaction. All right, the one more thing I want to talk to you about is, first off, this is the periodic table of elements. Elements are the purest of substances. These are not compounds. Compounds would be things like C6H12O6, which is glucose. That is the sugar or food plants make when they do photosynthesis with help of the light. Looking at this, we see there are 1, 2, 3 elements. And total number of atoms, well, there's 6 carbon, 12 hydrogen, 6 oxygen. But if we wanted to know how many atoms total, altogether, we're going to count 6. Plus 6 is 12. Plus 12 is 24. So there are 24 atoms total. If you are asked to count, remember to look at the subscript. If there's no subscript there, then that just means there's only one of the element present. Let us look at, let's say you were asked how many atoms of carbon are there. And you would say there's carbon is equal to 6 atoms, right? There's 6 atoms of carbon. All right. Another issue I wanted to address before we are done here today is the law of conservation of mass. The law of conservation of mass, and if y'all remember it correctly, it says what goes in, what? Must come out. That's right. So atoms are not created or destroyed during a chemical reaction. They just bond and rearrange themselves to create new substances when they bond. Let's look at a written example of that. So for example, if you have carbon and you have oxygen gas, which is O2, and these two reactants come together to make carbon dioxide gas. We still have, if we're looking at each side of this chemical reaction, we can see that here On this side, C is equal to 1 because we don't have a subscript. O, oxygen, is equal to 2 because there's a subscript of 2. So we had 1 carbon going into the reaction, 2 oxygen going in, and coming out we have carbon equal to, well, there's only 1, and oxygen equal to 2. So that proves the law of conservation of mass. The reactants, these are our reactants or input, and these are our products or output, are equivalent on either side of the chemical equation. And now we can say, yes, this is accurate. What went in came out. So this is an accurate representation of the law of conservation of mass. So let's look at some other ways you might see law of conservation of mass. You might see something like this on the test, where it shows you students mixing things together. They have a Ca, calcium chloride solution. Remember, always count those capital letters to figure out what we got. Every capital letter begins a new element, right? So they have this, and then they have NaSO4. They have this, and they actually balance them out before mixing them or allowing them to come in contact. One's in a test tube and one's not. And they masked it, and the mass of their reactants, because these are what's going to go into the chemical reaction, these reactants, these two substances, they masked it and they got a mass of 300.23 grams. They let the two come together by spilling over and allowing the two to mix. These two together are going to make, they are going to make CaSO4 and a white precipitate. Precipitate tells us chemical reaction, right? And they're going to have this and this present. All these elements, calcium, sulfur, oxygen, sodium, chlorine. Same as they had here, calcium, chlorine, sodium, sulfur, oxygen. They've just created a new substance with a precipitate. We know these are our products. This came out of the chemical reaction, and we have formed some new substances. Here, chemical reaction took place, and they mass it again, and the mass is identical. So this too proves our law of conservation of mass. What goes in are reactants, arrow to make products, or wrap. Reactants, arrow, products. Oops, P. That should be a P, guys. There you go. All right. You try one. You try one. Here's another example here. We have, once again, small test tube with some chemicals in it, some chemicals in the bottom of the flask. They mass it out, and mass is 67.25 grams. These are our reactants, arrow, products, wrap. And if we look here, we see that coming over here, well, let's look and see. Are there any indications a chemical reaction took place? Well, we can see there's some stuff in there now that they didn't have before. They had two liquids apparently, and now they have some solids. And it does give us that clue. A precipitate form, sign of a chemical reaction, yes. Now, they're massing it. It should come out to what? Should be equal. Atoms are not created or destroyed, right? So it should be 67.25 grams of mass. Now, what if the stopper had a leak or something like that, and we get an end mass of only 67? We're missing 0.25 grams. Well, that would indicate to us there was somehow some gas escaped. Most likely is what happened if we have, these are unequal, because they should be absolutely equivalent. because what goes in our reactants must come out as a product. I think that was it for our periodic table Staar Champions at Nolan Ryan Junior High hack. If I think of anything else, I will surely make an additional video to let y'all know. But I think that pretty much covers a quick review of our chemistry unit. Thanks for watching.